In this video, we are going to talk about what Simpson's rule is and how we can use it to approximate a definite integral. So the idea is we are going to approximate our curve with parabolas. So in the last video, we saw how we can approximate the curve using trapezoids, and now we're going to do it using parabolas. So let's draw a picture. So I will draw my axes. So let's draw some axes here, and then I'll draw some interval from A to B. And then I'm going to draw some functions graph on that interval. So maybe let's imagine that my function kind of goes down a little bit, and then it goes up, and then maybe it goes down, and then it goes up one more time. So I have this graph. And I'm going to cut up my interval into pieces. So it turns out that for Simpson's rule, I need to cut it into an even number of pieces. The reason for that is, to be able to draw a parabola, I need at least 3 points. And having 3 points kind of necessitates that, they come from like 1 and then 2 intervals. Every single time I want a parabola, it's got to come from two subintervals. So I'll need an even number of subintervals. So in my drawing, I'm going to go ahead and draw, let's see, 1, 2, 3, 4, 5, 6. I'll draw 6 of these subintervals. Let me label these points. So where A is, I'll call that x0, and then I'll have x1, and then x2, up until B, which we call xn. All right, and now let me go ahead and draw some of these parabolas. So for this first set of subintervals, I need to take 2 of them, because I need 3 points to make a parabola. So I'll draw 1 point, my second point, my third point. So if I do my best to kind of connect those 3 points with a parabola, that might look something like this. It might look something like maybe the parabola, something like, I don't know, maybe it's something like this, and then it goes up, and it does something like that. So I'll have a parabola like this. So the parabola is, pretty close to what the curve is. All right, and then let me draw 3 points, in this next set of 2 subintervals. So I'll draw this one that I already have, then this one, and then this one. If I connect those with a parabola, we'll get a downwards facing parabola. So that might be something like this. Ooh, I don't love that drawing. One sec, let's make that a little better. So maybe that's something like this, where it goes down, and then over here. Okay, so I got a parabola, and then I got one more set of subintervals, these last 2 here, and I'll switch it to a different color. So I got 1 point, a second point, a third point. If I connect these with a parabola, maybe that parabola now is looking something like, don't love this drawing, but maybe it's something like, I have a vertex here or something, and then it's doing something like this, and then going up. It's not perfect, but something like that. We get the gist, hopefully. So we're creating these parabolas to approximate the curve. So I'm going to denote this whole, if I were to look at the areas under each of these parabolas and add them up, I'm going to denote that by S subscript n. So that's the area using Simpson's rule when we have n subintervals. We already noted that n has to be even. I need an even number of pieces to be able to create parabolas like this. It turns out, if you do a decent amount of algebra, that Sn ends up being given by the following formula. We saw a very similar formula when we were using the trapezoidal rule. Remember, delta x, that's the width of one of these subintervals. So my delta x. And then I get something like this, where it's like f of x0. So I plug in this first, point, this left endpoint into the function. And then after that, the coefficients kind of alternate 4, 2, 4, 2, and so on until I have a 4 second to last one. And the very last one, with this right endpoint, the coefficient is just 1. Okay, so I won't do the derivation of where this formula comes from, although you can find it in our textbook if you're curious. I'm going to focus mostly on applying this. So let's get right into an example. Let's suppose I want to estimate the integral from 1 to 3 of e to the 1 over x with Simpson's rule and n equals 8. round this thing to 6 digits. So to be able to use Simpson's rule, I need to know what all of these x values are. So let's draw a number line. Let us draw a number line. Let's draw a number line. And then I'll draw my interval, which starts at 1 and goes until 3, and I'll split it up into 8 pieces. So I can cut it into half, I can cut it into quarters, and then each of those I can cut into halves again. So halves, 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 halves. Now I have 8 pieces. And, to find my delta x is b minus a on top, divided by n, which is 8 here. So this becomes 1 over 4. 1 over 4, which as a decimal is 0.25. So if I add 0.25 to the 1, I'll get the value 1. Let's go to draw mode, 1.25 for this tick mark. And if I add 0.25 again, I'll get 1.5. And if I keep doing that, next up I get 1.75, then 2, then 2.25, then 2.5, then 2.75, and then if I do it again, I get to 3. Okay, so I got all of those values. Now I'm actually ready to plug into this formula. So in this case, it's s sub 8. We're using 8 subintervals. Simpson's rule says do delta x divided by 3. So delta x is 0.25. Divide that by 3. I'll put a big old parentheses. And now I have to, plug in x naught, which was this left endpoint, into my function. So my left endpoint is 1. That's my x naught here. I got to plug that into the function. So if I do that, I'll get e to the 1 over, and now I'm plugging in 1 for the x. Okay. All right, next up, I'll have 4 as the coefficient times what I get when I plug in the next, tick mark value into my function. If I plug that in, I'll get e to the 1 over, I'm plugging in 1.25 for the x. All right. Next coefficient's a 2, so I'll get plus 2 times, and now I plug in 1.5 into the function. So 2 times e to the 1 over 1.5. So we're going to keep going in this way, alternating coefficients with 4 and 2 and 4 and 2 until I get to the end. All right, so next up I'll have plus 4 times, and I'm going to plug in 1.75, e to the 1 over 1.75. Next up I'll have 2 as the coefficient, times e to the 1 over, now I'm plugging in 2 for the x. Then the coefficient switches to 4, times e to the 1 over, we'll plug in 2.25, 2.25, and then the coefficient switches to 2, times e to the 1 over, plug in 2.5. All right, we're getting close to the end. Now we do plus 4 times e to the 1 over, we're plugging in 2.75. All right, and we're reaching the end. When you reach the end, the coefficient's just a 1. You don't write anything in front of it. So now I'll just get plus e to the 1 over, and I'm plugging in 3. And it should end up happening that as long as I set it up correctly, once you get to that ending one, the one before it should have had 4 as its coefficient. All right, so we have this. If I, use a calculator to work this out, and I approximate it, this is approximately 3.52237,467. If I just go to a bunch of decimal places. My problem said round it to 6. So if I round it to 6, what's the 6th decimal digit? It's this 4. So the number after that was a 6. That's going to force it to round up. So that'll give me, my integral is approximately 3.5223.7, and then round up that 4 to a 5. Okay, and I have my approximation. That's the answer to part A. Just like we did with the trapezoidal rule, we can talk about the error of our approximation with Simpson's. So I'm going to denote the error using Simpson's rule by E subscript S. That's going to be the difference between the actual integral, the actual area, minus Sn, minus the approximation we just got. So there's a theorem that says the absolute value of that error is less than or equal to this fraction. So we had a very similar fraction for trapezoidal rule. There's this variable here, k, which is an upper bound now for the absolute value of, this is the fourth derivative of f. So that means the absolute value of my fourth derivative is less than or equal to k on this interval that we care about. I'm not going to prove this thing, but if we did need to, we can prove it with the mean value theorem. I'm going to focus more on applying it with an example. All right, so how do we use this? Let's do an example. So now for that same example, let's find an upper bound on the error. To be able to use this theorem for the upper bound, I need to first find k, which is an upper bound for the absolute value of my fourth derivative. So I've gone ahead and worked out what the fourth derivative is. It's given by this fraction. So let's use that to find k. So the first thing that I want to, notice about this is, so if I have to take the absolute value of this, I take the absolute value of the other side. And when I do the absolute value of the right, I can just do the absolute value of the top over the absolute value of the bottom. Like that's the same. So even though this is less than or equal to here, even though it says that, technically this is an equal sign. So I can even cross this out. Technically this is an equal sign. I haven't changed anything about this. Now, let us go ahead and I'm going to do two things. I notice that this e term is multiplying that whole thing. So I can split it up first as absolute value of e to the 1 over x times the absolute value of all that other stuff. I'll just put a squiggly line for all that other stuff. And then all over the absolute value of x to the 8. Now for all the stuff that's in here, all of these things that were in the parentheses, well, those things are being added. I can now do triangle inequality on those. So by the triangle inequality, remember the triangle inequality says when you have absolute value of a plus b, that's less than or equal to the absolute value of a plus the absolute value of b. We saw that in the last video. So I'm going to keep that e term as it is. And then with this thing in this absolute value, all these things added together, I'm going to split it up and use my triangle inequality to say, okay, I'll get the absolute value of the first thing, plus absolute value of the second thing, plus absolute value of the third, plus, and there's 4. So I'll get 4 absolute values added together. It's 24x to the 3 in the first, and then it's 36x squared in the second, 12x in the third, and then just 1 in the last one. All over my denominator, that absolute value of x to the 8. So we're using the triangle inequality on this stuff in parentheses, and that has become this after we did the triangle inequality. So notice this is not an equal sign, it's an inequality. So now I'm going to think about these absolute values kind of piece by piece. My goal is to, have this fourth derivative's absolute value, and I got that it's less than or equal to this thing, to hopefully get that's less than or equal to something, and eventually get that this is going to be less than or equal to just some number, no x's. Because when I get that, this is going to be k. So I want to continue this inequality, so I want to find something that's bigger than what I have. So these terms on the numerator, if I'm trying to make the whole fraction bigger, I got to make the ones in the numerator bigger. So my interval for this problem was from 1 to 3. My interval is from 1 to 3. So what number in that interval would I plug into this e term to make it as big as possible? We'd plug in 1. Okay, so if I did that, I'd get e to the 1 over, plugging in 1 for that other x, I'd get this. So I'd get this, it's in an absolute value. And then big old parentheses, and then I have these other absolute values. So what would I plug into those from this interval to make them as big as possible? Well, for each one of them, we'd actually plug in 3. If you plug in 3 into all those x's, it makes it as big as possible. So that first absolute value, and in fact, once I plug in 3, all these things are positive, so I don't need to write absolute value. So I can just write 24 times 3 cubed plus 36 times 3 squared, plus 12 times 3, and then plus that 1. So overall, I'm replacing each of these terms in the numerator with something that's, bigger than it, something that's greater than or equal to it. On the denominator, I have to replace it with something smaller than it, because to make a whole fraction bigger, I need to make the denominator smaller. So what value in this interval makes that denominator as small as possible? Well, it's 1. And if you plug in 1, you'll get 1 to the 8th. I don't need an absolute value because this is already positive. All right. So if I simplify this, we get 1009 times e, because there's this e term here. So that is my value of k. K is just, I'll put this in a different color, it is 1009e. All right. So in that last video, we saw another method for finding this value of k, which is, take this function, plug it into a graphing calculator, and use that to find this upper bound. I wanted to do this the harder way to practice that a little bit, because we won't always have the luxury of a calculator. So we can do this using this inequality algebra. All right, so now let's take that value of k, let's plug it into our error formula. So we got this value of k. I'm going to plug that into that numerator. So if we do that, we get that this equals k times, so b is 3, a is 1, and then to the 5th, all over 180 times, and then the value of n for the problem was 8. If you plug this in, this ends up being approximately equal to 0.119043. It said to find an upper bound for the error, and at this point, that's what we got, an upper bound for my error. So what this tells us is the approximation that we got with Simpson's rule, well, at worst, it's off by this much, by 0.119043. Okay, so pretty decent. If I wanted to get a more accurate estimate, we would have needed to split up our interval into more pieces. All right, so that next question is now related. What's the smallest value of n, the smallest number of pieces I could split into, so that our Simpson's rule approximation would be accurate to within 0.001? So what I want for this is my error. I want this error, which is less than or equal to this. So let's set this k times b minus a to the n over 180 n to the 4th. I really want that to be less than or equal to 0.001. I want it to be less than or equal to this. All right, and now let's try to work with this and solve. So I have k times 3 minus 1 to the, oh, and whoops, I think I miswrote something. I wrote this exponent, it should have been a 5, but I just wrote n, so let's fix that. So let's fix that. That should have been a 5. I get 3 minus 1 to the 5th. On my denominator, I have just like 180, and then I'd have the n to the 4th. So what I'm going to do is rearrange some terms. I'm going to divide this 0.001 over to the other side. So divide by 0.001. And then I'll multiply n to the 4th over to this side. So I'm trying to isolate the n. All right, so what we're getting now, let me just write the n part first. N to the 4th is greater than or equal to this whole fraction. If you plug in the value of k that we got, and we plug that in for the k, and you work this out with a calculator, you get that this is 487,599.35. All right, so now if I fourth root both sides, you'll get n is greater than or equal to 26.4. So, okay, so to guarantee that this approximation is accurate within 0.001, I need n to be greater than or equal to 26.4. So what's then the smallest thing that n could be? So n's got to be an integer. It's the number of subintervals. It might be tempting to say 27, but remember that we said at the start of the video that n has to be even. So the smallest even number that's greater than or equal to this is 28. And we got it. That's our smallest value then. This must be even.